Today we're going to look at how to use the information we gather, as well as Lewis structures, to represent an ionic, a polar covalent, and a non-polar covalent bond. We start by using our electronegativities to calculate our percent ionic character to get our bond type. So I know a bond between calcium and chlorine is 63.2% ionic character, so it is an ionic bond. The next step is I draw my Lewis structure for each element. Calcium is an alkaline earth metal, so it has 2 valence electrons. Chlorine is a halogen, so it will have 7 valence electrons. In an ionic bond, we have a complete transfer of an electron. Each element wants 8 valence electrons, so it will either give up or take electrons to obtain 8. The more electronegative element will be the one that takes the electron. In this case, chlorine has an electronegativity of 3.0, so it will be taking an electron from calcium. Since chlorine already has 7 valence electrons, it wants 1 more, so it's going to take 1 electron from calcium. The way we represent that happening is using a curved half arrow. So think back to when we were doing orbital diagrams, we mentioned we use half arrows to represent single electrons. So we use a curved arrow, it's only a half arrow, to represent that 1 electron moving. So I've used a curved half arrow, only 1/2 of the head, to represent an electron moving from calcium to chlorine. So now I can redraw my Lewis diagram. Chlorine has gained an electron, so now it has 8 valence electrons. Normally chlorine has 17 protons and 17 electrons. Since it has gained an electron, it now has 18. I now have 17 protons and 18 electrons for chlorine. If we remember, protons are positively charged, electrons are negatively charged. Let's use a symbol to represent each one. I'm going to use a plus symbol to represent each positive charge. We'll use a minus symbol to represent each negative charge. So protons will be the plus symbol, electrons will be the minus symbol. We'll draw 17 pluses and 18 minuses. So now I have 17 positives, 17 protons, and 18 electrons represented. I'm going to cancel out 1 positive with 1 negative. We'll continue doing this until I've run out of one or the other. After I've finished canceling, I'm left with 1 extra negative charge. The way we show that in our Lewis diagram is by putting a negative symbol in the upper right of the diagram. Now let's take a look at calcium. Calcium normally has 20 protons and 20 electrons, but it lost an electron. So now it will have 20 protons and 19 electrons. I could draw it out and cancel out just like I did before, but looking at it, I recognize that I have an extra proton. Protons are positively charged. I have 1 extra proton. So I represent that with a plus symbol in the Lewis structure. When we are making a bond, each element wants 8 valence electrons. Chlorine now has 8 valence electrons. It's happy. It's in a stable configuration. But calcium now only has 1 valence electron. When you have 1 valence electron, you're similar to an alkali metal. And alkali metals are very, very reactive. They really want to get rid of that 1 electron. The other thing that we typically consider is when we're creating a bond between elements, we can't really just have 2 atoms. Atoms are too small. We have a lot of calcium atoms and a lot of chlorine atoms. So anytime that we are making a bond, there's excess of the other kinds of atoms around. So calcium still wants to get rid of one. It's going to find another chlorine atom that still wants to take one. So when calcium finds its next chlorine atom, it's going to give up its electron. Again, we represent that with a curved half arrow. To chlorine. So calcium has given up its electron to chlorine. Let's redraw it. So now this chlorine has gained an electron, just like this one, so it will have a negative charge. Looking at calcium, though, I'm not sure how many valence electrons it'll have, because it's given away its 2 electrons. Let's look at the orbital diagram for calcium to help us figure this out. So in a neutral calcium atom, its valence energy level is the 4th energy level. It's the highest one. Calcium's given up its 2 valence electrons, though. So it no longer has electrons in the 4th energy level. Since it doesn't have electrons there, it can't be its valence energy level. The highest energy level that calcium has electrons now is the 3rd one, the 3p and the 3s. We have 2, 4, 6, 8. So calcium now has 8 valence electrons. It has achieved a stable electron configuration. But now we've got to consider charge. Calcium has given up 2 electrons. When it gave up 1, it had a positive charge. If it gives up 2 electrons, it'll have 2 positive charges. Because now it'll have 20 protons and 18 electrons. It has 2 extra positive charges. The way we show that is to put a 2 plus. And you'll notice I wrote the 2 before the plus. These are charges, not positive and negative numbers. By writing the 2 first, that helps us remember that this is 2 positive charges rather than just positive 2. So we have 2 positive charges on calcium. So the final Lewis structure for the ionic bond between calcium and chlorine is this right here. We show the calcium ion now, since it's charged, with a 2 positive charge, and each of the 2 chlorine ions with their negative charge, all having 8 valence electrons. Next up, we're going to take a look at a polar covalent bond. Next up, we're going to look at the bond between hydrogen and oxygen. Hydrogen has an electronegativity of 2.1, oxygen is 3.5, my delta E neg 1.4, so my percent ionic character is 38.7%. And this is a polar covalent bond. Again, I need to start with my Lewis structures. Since hydrogen is in group 1, it only has 1 valence electron. Oxygen is in group 16, so it will have 6 valence electrons. Again, we need to remember that each element wants a full valence shell. For all elements other than a handful, that's 8 valence electrons. Hydrogen, if it gets 2 electrons, has a full energy level since it only has the first energy level. Since hydrogen only uses the 1s orbital, it is full with 2 electrons. There are 2 different ways you can represent a covalent bond being formed. A covalent bond will form between unpaired electrons in the Lewis structure. So the unpaired electron with hydrogen and an unpaired electron with oxygen will form a covalent bond. There's 2 different ways you can represent it. The first one is using curved half arrows pointing in between them. So each electron is shown moving to the middle because covalent bond is a sharing of electrons. They move to the middle, so to speak. The other way you can represent a covalent bond forming is by circling the unpaired electrons. So this circle here represents a bond forming between that electron and that electron. To represent this in a Lewis structure, we use a solid line. So this line right here means that we have formed a bond between hydrogen and oxygen. Each line represents a pair or two electrons. So hydrogen gets access to these two. Remember, it just has the first energy level, so it's happy or stable with two. So hydrogen has a full energy level. Because they're being shared, oxygen also gets access to them. So now oxygen has 2, 3, 4, 5, 6, 7. So oxygen isn't happy yet. It's not reached a stable configuration. Again, remembering we're never going to be able to make a bond between two atoms. We have lots of each. Another hydrogen is going to find its way to oxygen. So we've added another hydrogen. It has an unpaired electron. Oxygen still has an unpaired electron. Let's make a bond between them. So we make a bond between each of those unpaired electrons, and we're going to redraw it using a solid line to represent that bond. So let's check to make sure everything has the correct number of electrons. These two electrons belong to both hydrogen and this oxygen. Hydrogen gets both, access to both, so it is stable. Oxygen gets these two. Hydrogen and oxygen are sharing these. Hydrogen gets access to them, so it'll have its two to be stable. Let's count how many oxygen has now. Oxygen has 2, 3, 4, 5, 6, 7, 8. So oxygen has gotten its 8 valence electrons. It is happy. It has reached a stable electron configuration. Really quickly, we need to talk about the polar part of this covalent bond. The polar means that this is not an equal sharing of electrons. The more electronegative element will have the electrons more often. It pulls those electrons toward itself much stronger than the less electronegative element. Not enough to completely separate them from the other element, but still strong enough that there is a slight charge on the element. And by slight, we say it is a partial charge. The more electronegative element will have the partial negative charge. The less electronegative element will have the partial positive charge. This is a Greek letter. It is a lowercase Greek delta. The lowercase delta will mean a partial when we write it with a charge. Interesting bit of information, the triangle up here is the uppercase version of the Greek delta. So I'm going to use this symbol with the negative after it to represent a partial negative charge. So oxygen now has a partial negative charge, and each hydrogen will have a partial positive charge. And just like with showing full charges in an ionic bond, I show that in the upper right of the symbol. Next up, we're going to look at a nonpolar covalent bond. Lastly, we're going to take a look at a nonpolar covalent bond. I have carbon and iodine, each with an electronegativity of 2.5, so my delta E neg is 0.0. I get a percent ionic character of 0%, which gives me a nonpolar covalent bond. Again, I start with the Lewis dot diagrams because carbon is in group 14. It has 4 valence electrons. Iodine is a halogen, so it will have 7 valence electrons. Again, you can either use the curved half arrow or circles to represent a bond forming. I look for unpaired electrons and pair them up. Remember, we use a line to represent this bond forming. So remembering each element wants 8 valence electrons. Each of them get access to the bond since they're sharing. Iodine has 2, 4, 6, 8. Iodine is happy. It's reached a stable configuration. Carbon has 2, 3, 4, 5. So it doesn't have its 8 yet. It's going to find another iodine to bond with. So I put another iodine in, I make another bond, and we'll redraw the Lewis structure. Now I have this iodine still has 8. This iodine has 2, 4, 6, 8, so it's reached a stable configuration. Carbon now has 2, 4, 5, 6. Still not there, let's put in another iodine. So I'm going to add in another iodine, but I'm sensing a pattern here. I still see an unbonded electron here. Let me count just to make sure. So I know iodine will be happy, they're always happy when I make one bond. But carbon has 2, 4, 6, 7. Let me try putting another iodine in, see what that does. So added a fourth iodine. Again, it's just like all the others, it has its 8 valence electrons. Let's count for carbon. Carbon has 2, 4, 6, 8. So now it has its 8 valence electrons. It has reached its stable configuration. So let me redraw it using the lines to represent the bond. So this is the final Lewis structure for the bond between carbon and iodine. Carbon has made a bond to 4 different iodine atoms. Each iodine atom has its 8 valence electrons, 2 from the bond, plus its 6 own. Carbon's 4 bonds at 2 electrons each adds up to 8 valence electrons. Nonpolar covalent means that it is an equal sharing of electrons. None of them are stronger in pulling the electrons away from the other. Since there is an equal share, neither of these atoms is going to even have a partial charge. They're still going to be neutral. Since it is an even sharing, we don't have to represent any charge, any partial charge. This is the completed Lewis structure. In summary, if we have an ionic bond, one element takes the electron away from the other, gives it a full positive or negative charge. The element that takes the electron will be negatively charged. The element that gives the electron away will be positively charged. We show that just by representing dots. For a covalent bond, we use a line to represent a sharing of electrons between 2 elements. If we have a polar covalent bond, there's an unequal sharing. One element will have it more than the other, so it will have a partial negative. The more electronegative element has a stronger pull, so it's going to have a partial negative. The less electronegative element will have a partial positive. For a nonpolar covalent, it's an equal sharing. They each get it the same amount of time, so there is no overall charge.